Hello everyone. Welcome back to Pallence AI and welcome back to the Deep Learning Foundation series. In the last video, we talked about activation functions, the nonlinear functions that help neural networks learn complex patterns. Today, we are moving to another essential idea, how a model actually measures its mistakes. Mistakes? Yep, you heard right. How do we humans best learn anything in life? Through our mistakes. Yeah, it's a whole different thing. Not many do. That's a different thing. But machines or these AI models, based on deep learning, they learn from their mistakes. In fact, as anyone who aims to be intelligent needs to do. Every neural network or a deep learning model, just like we or many humans learn from their mistakes, which we sum up as losses. Now, whether a deep learning model is recognizing digits or powering a large language model, deep learning models learn by reducing one thing, its loss, which is nothing but sum of all the mistakes and errors which these models make in their training process. But they do this in the hope of finding best weights or parameters and in the process become intelligent. If it helps, just focus on this simple intuition. Think of loss functions are like the GPS the model uses to find better weights that can make them very smart or intelligent. Let's learn now about loss or cost functions, which are nothing but a measure of error between y pred and y. Y pred being the model's prediction and y being the actual y. Just to recap again, if we see this, the schematic for the intuition behind deep learning algorithm, you see the loss function here, right? So this is a measure of what the model is predicting as y is, the y pred, and the actual y. So loss function is the loss on the error for a single image. So if you sum up all these losses and divide it by the total number of images, you get the cost function, right? So let's see what are the different types of loss or cost functions that are used in deep learning and machine learning. Okay, so let's start with very simple one. Okay, so for regression, we have a loss function called mean square error. Again, when it comes to machine learning, right, we have regression or we have classification. So if you're dealing with regression problems, we can use a loss function like mean square error. This is also easy to understand. So this is the mathematical equation for mean square error, right? What are we doing here? So we are calculating the difference between what the model predicted, the y pred, and the actual y. We calculate the difference and we square it. And then we sum this loss for all the images. So n being the total number of samples in your data set. So sum of squared errors, right? And then you divide by the total number of samples, and that would be your total cost. So if we want our model, to come up with a very good prediction, y pred, right? We want the difference between y pred and yi, the actual y, to be very close, meaning the j should go to 0, right? So that's what the model is trying to do, and it tries to, optimize those weights that can make this cost function go to 0. Okay, so for regression problems, typically algorithms, machine learning and deep learning algorithms use a mean square error cost function. Okay, all right. So now let's talk about the binary classification, right? Like for example, in the earlier videos when we were talking about the machine learning problem, when we were trying to explain how a machine learning algorithm works, we're trying to determine whether an image is human face or not, right? It's a binary classification problem, or some, you can say, whether a MRI or, a mammogram has breast cancer, yes or no. So again, you can have many different types of binary classification problems. So for that, we use a loss called binary cross-entropy loss. Again, don't get, again, if your math is a little bit rusty, don't get too much scared with this equation. All we are trying to do is we're trying to come up with some kind of a measure as to how good the model is predicting the y. Again, looking at the mean square error should give you a clear idea here, what the model is trying to achieve. So for binary cross-entropy loss, this is the equation we use. But bottom line, think of it as some kind of a measure of error or a penalty, between the model's prediction and the actual prediction. So we sum up all these losses for all the images, divide by the total number of samples, and we get the total cost, total penalty. Okay, all right. Now for multi-class classification problem, we use a different loss called categorical cross-entropy loss. So again, don't get too intimidated by the equation. Bottom line, if you are using multi-class classification problem, instead of using binary cross-entropy loss, use categorical cross-entropy loss. Okay, especially when your y labels are one-hot vectors. So I'll go back to the schematic just to explain in case you forgot what these one-hot vectors are. But if you're using the y labels, your classes, if it's a multi-class classification problem and your y labels are one-hot vectors, use categorical cross-entropy loss. Okay. Whereas if, again, for the multi-class classification, if your y labels are just integers, then you use something called sparse categorical cross-entropy loss. Again, don't worry too much about the equation. Again, in later videos, like when we actually implement many deep learning models, we're going to use these different losses, to train our models. Okay. But again, what are these one-hot vectors and the integers? If we just go back here, right, remember, when we were trying to do the pre-processing for a data set, you look at the y-train labels, the image 2, for the image 2, the label was just 2, integer 2. But instead, I explained this intuition by converting this label 2 into a one-hot vector of 10 classes. If in your data set, if your labels are these one-hot vectors instead of integer labels, right, then use, categorical cross-entropy loss. But whereas if your labels are integers, right? If your labels are integers, then use the sparse categorical cross-entropy loss. But again, don't worry, we're not going to implement these loss functions by hand in Python or anything, because all these loss functions come pre-built with the TensorFlow and Keras, which is what we're going to use in this course. But even if you use PyTorch, there will be similar ways where you can directly incorporate all these losses as you're building your deep learning models. Okay. Hopefully, this video helped you in understanding the concept of loss functions a little better. The part of neural network that tells it how wrong it was. In the next video, we'll bring everything together by looking at something called gradient descent, the engine that actually minimizes this loss, and how in the process it makes the model very smart as the loss goes to zero. This lesson was again part of my Deep Learning Mastery course on Udemy, and I've linked the full course below if you want a complete hands-on path to learn deep learning. And if you found this particular video helpful, please feel free to subscribe. I'll publish even more foundational AI videos to help you truly understand what's happening under the hood of all this powerful deep learning, neural network, or AI models. Thank you so much for watching. Happy learning, and I will see you in the next one.